Look up at the night sky tonight. Whatever you picture as the scale of the universe is wrong, not slightly wrong, not off by a factor of 10, wrong by margins so enormous that human intuition simply shuts down trying to process them. Astronomers just confirmed a superstructure called Quipu, stretching 1.3 billion light-years with the mass of 200 quadrillion suns, and it still represents only a thin thread in something vastly larger. Every time scientists think they have found the biggest thing, a bigger thing appears behind it. We have been measuring our place in reality with a ruler designed for measuring rooms, and tonight I am going to destroy that ruler. What you learn next will break the way you see everything above your head. If you enjoy journeys that expand the way you see existence, take a moment to hit that like button and subscribe. Now, settle in, get yourself comfortable, let's begin. Hold up your hand in front of your face. Really do it. Look at your palm, your fingers, the lines crossing your skin. That hand is the ruler your brain was built with. Every sense of distance you have ever owned comes from that hand and the body attached to it. You understand how far you can reach. You understand how far you can walk in an afternoon. You understand, roughly, how long it takes to drive across your country, because somewhere in your head is a map assembled out of hours and hunger and tired legs. This is the ruler evolution handed you. It works beautifully for finding food on a savanna. It fails almost immediately, the moment you point it at the sky. Let me show you how it fails. Start with something simple. Imagine you want to walk from one side of your town to the other. Depending on where you live, that takes maybe an hour. Now imagine walking from one side of your country to the other. Depending on the country, that takes weeks, months, years. Now imagine walking all the way around the Earth. At a steady pace of about 3 miles an hour, never stopping, never sleeping, you would need around 1 year to circle the planet along the equator. 1 year just to trace a single loop around the rock you live on. That is already a number your brain struggles with. Most people have never walked more than a few hundred miles in their entire life. The size of Earth is, for almost every human, already abstract. We have just barely begun. Now lift your eyes from the ground. Earth is a sphere roughly 8,000 miles across. That is an enormous object from your perspective, but let me compress it for you. Let me shrink the Earth down until it is the size of a small marble, about the diameter of a pea. Hold that pea in your hand. At this scale, every ocean, every continent, every mountain range, every city, every person who has ever lived, every war, every love story, every piece of music ever written, every thought you have ever had, all of it fits inside a sphere the size of a pea in your palm. 8 billion humans, hundreds of thousands of years of history. A pea. That is your home at the scale we are about to start using. Remember the pea. We are going to need it. Now, at this pea scale, where is the moon? The moon is the closest object to Earth in all of space. It is the only other world any human has ever stepped on. It is the thing that lights your night sky and pulls your tides. You might assume it sits a finger's width away from your pea. It does not. At this scale, the moon is a grain smaller than the pea, and it hangs about 7 inches away from your hand. 7 inches. Empty space between. The distance the Apollo astronauts crossed in the late 1960s, a voyage so ambitious it consumed the entire budget of a superpower, is 7 inches in pea units. And even that 7 inches is almost entirely nothing. Vacuum, darkness, a few drifting particles. If your pea is Earth, then the gap between you and the moon is already mostly a desert. Good. Your ruler is already beginning to bend. Let us keep going. Now introduce the sun. The sun is the star our planet orbits. It is the furnace that powers every weather pattern, every photosynthesizing leaf, every bite of food you have ever eaten. It is unimaginably huge compared to Earth. You could fit about 1,300,000 Earths inside the sun. Think about that for a moment. If Earth is your pea, the sun is not another pea. The sun is a beach ball, and the beach ball is not 7 inches away. The beach ball is roughly 230 feet away. That is nearly the length of a football field. Your pea, representing everything humanity has ever done, sits on one end of a football field. The sun, the engine of everything you are, burns on the other end. I want you to really sit with that. On a true scale model where Earth is a pea, you cannot reach out and touch the sun. You cannot see the sun clearly from the pea. You cannot hold both in the same hand. You have to walk, and the walk is nearly 230 feet of empty air. Light, the fastest thing the universe allows, takes about 8 minutes and 20 seconds to cross that gap in reality. Not instant, not negligible. 8 minutes. If the sun vanished right now, you would continue feeling its warmth for over 8 minutes before the sky realized something was missing. The speed that physics calls infinite in everyday terms already takes meaningful time at the scale of a single star system. Now let us build the rest of the solar system on this football field. Mercury, the innermost planet, is a tiny sand grain about 90 feet from the beach ball sun. Venus, roughly the size of Earth, is another marble at around 160 feet. Your pea Earth sits at 230. Mars, smaller, reddish, a favorite of science fiction, is another marble about 350 feet out. You have already walked past home plate in baseball terms. You have already crossed the length of a large building, and the solar system is only just starting. Jupiter. Jupiter is the real monster of our local neighborhood. It is a gas giant so massive that every other planet combined still does not equal it. On our scale, Jupiter is a grapefruit, and the grapefruit is about 1,200 feet from the beach ball sun. That is nearly a quarter of a mile. Let me translate. You have to walk 4 football fields end to end before the grapefruit appears. Between the inner marbles and the outer grapefruit is almost pure emptiness. No planets, just a thin belt of scattered rocks called the asteroid belt, which in movies looks like a crowded minefield but at true scale is so sparse that spacecraft fly through it without ever seeing anything bigger than a pebble. Emptiness, again, emptiness. Saturn, the ringed jewel, is another grapefruit about 2,200 feet out, almost half a mile. Uranus is further still, a smaller fruit roughly 4,400 feet away, nearly a full mile from the sun. Neptune, the outermost of the classical planets, sits roughly 8,000 feet out. That is about a mile and a half. Imagine standing next to a beach ball and knowing that one of the planets in your own solar system, the last great gas giant, is represented by something you could not even see without binoculars, sitting over a mile away in the distance. And between the beach ball and that distant dot, the map is essentially empty. The solar system at this scale is not a crowded cosmic neighborhood full of worlds. It is a single lonely fire, surrounded by a few tiny marbles and a lot of darkness. That is the first major shock your ruler has to absorb. Space is not full of stuff. Space is defined by the stuff not being there, and we have not even finished the solar system yet. Far beyond Neptune stretches a region called the Kuiper Belt, where Pluto and thousands of icy bodies drift through a twilight so thin the sun appears only as a particularly bright star. Beyond that lies the scattered disk. Beyond that, theorists believe, lies the Oort cloud, a spherical shell of dormant comets that may extend out to 1 light-year from the sun or more. 1 light-year? We have not even reached another star yet, and already we are invoking a unit of distance so enormous that it describes how far light itself can travel in a full Earth year. The Oort cloud, if it exists as imagined, marks the true edge of our sun's gravitational neighborhood, and it takes a photon 12 months to cross just a fraction of it. Let me be more precise about Voyager, because its status as of right now is worth pausing on. Voyager 1 crossed the heliopause, the boundary where the solar wind can no longer push back against the particles of interstellar space, in August of 2012. It has been in interstellar space for over a decade. Its radio signal, beamed back to Earth from beyond the heliopause, currently takes more than 22 hours to reach us, moving at the speed of light. 22 hours one way for the fastest possible signal from the farthest object humans have ever made. And Voyager is still, by any cosmic standard, practically in our front yard. It has not even begun to approach the inner edge of the Oort cloud. At its current speed, Voyager will take roughly 300 years just to reach the beginning of the Oort cloud, and perhaps 30,000 years to cross through it. The probe that represents 50 years of sustained engineering achievement will need 30,000 more years, give or take, simply to exit the Sun's gravitational neighborhood. And when it does, it will not be heading toward any particular star. It will drift in roughly the direction of the constellation Camelopardalis for tens of thousands of years before passing within a light year or two of any other stellar system. The golden record attached to it, meant for any alien civilization that might one day find it, will likely never be read, because the distances between stars are so vast that Voyager, despite its blistering speed, is essentially standing still from a galactic perspective. The ambitious probe that represents the peak of human space engineering is, on the cosmic map, a frozen object drifting through an almost infinite sea of darkness, and it will remain essentially motionless for longer than recorded history has existed. Here is a number that might help anchor you. Voyager 1, a spacecraft launched in 1977, is the fastest, farthest human object ever built. It has been flying outward for nearly 50 years, moving at about 38,000 miles per hour. That is not a typo. 38,000 miles per hour. Fast enough to cross the continental United States in less than 5 minutes. Voyager is currently about 15 billion miles from Earth. It has crossed the heliopause, the boundary where the sun's wind fades into interstellar space. It is the farthest thing we have ever made. And yet, if you were to point Voyager at the nearest star system and tell it to keep going at its current speed, it would take approximately 73,000 years to arrive. 73,000 years. Civilization itself is only about 10,000 years old. The pyramids are less than 5,000. Voyager's journey to the next star, at our fastest achievable speed, is 7 full civilizations end to end, and that is the closest star. So let us talk about the closest star. Our Sun, the beach ball, is a member of a loose swarm of stars in a spiral galactic arm. The nearest known star to our Sun is a small dim red dwarf called Proxima Centauri, part of the Alpha Centauri triple system. It lies approximately 4¼ light years away. 4¼ years at the speed of light. And remember, at our scale, light already took 8 minutes to cross a football field. How far away does 4¼ light years sit on our football field model? Are you ready? On the scale where Earth is a pea and the Sun is a beach ball at 230 feet, Proxima Centauri is another beach ball-sized star sitting approximately 11,000 miles away. 11,000 miles. That is not a typo either. If you set up your beach ball sun in New York City, the next beach ball star would sit in Sydney, Australia, with nothing but hollow space between them. You would cross every ocean on Earth to reach the neighbour. Our entire solar system, every planet, every moon, every asteroid, every comet, every probe we have ever launched, every dream we have ever had of colonies on Mars or mining the outer planets, fits into the tiny region right around the first beach ball. The rest of the journey to Sydney is empty. Think about that the next time you look at the night sky and see stars that look close together. They are not close. They are unimaginable distances apart, separated by voids that dwarf anything human activity has ever touched. And yet, this is only the beginning. Let me stress this because it matters. Everything I have just described, every marble, every grapefruit, every mile of empty space between Neptune and the Oort cloud, every stunning realization that Voyager will take 70,000 years to cross the gap to the next star, all of that fits inside the tiniest corner of what comes next. The solar system is not even the first step on the ladder. The solar system is so small on the scale we are about to enter that it vanishes completely. Not gets small, vanishes, becomes invisible, disappears from the map. Before we leave this scale, I want to do one more thing. I want to put the speed of light in context, because light speed is the most abused concept in science communication, and the reason it gets abused is that humans have no intuition for how slow light is at cosmic scales. In everyday life, light is instantaneous. Flip a switch, the room is bright. Call a friend across the country, your voice arrives in a heartbeat because the signal travels at a fraction of light speed. For a long time, humanity assumed light was infinite in speed because it appeared that way. It is not. Light is finite, and in space, that finiteness ruins everything. When you look at the sun, you are seeing the sun as it existed 8 minutes and 20 seconds ago. If a solar flare erupted on the surface right now, in real present time, no telescope on Earth would know about it for over 8 minutes. When you look at Jupiter in a backyard telescope, you are seeing Jupiter as it was roughly 40 minutes ago. When you look at Neptune, you are seeing light that left the planet about 4 hours earlier. The outer edge of the Oort cloud, if it exists at the predicted distance, shows us photons that departed a year ago. Already, inside our own solar system, we cannot see the present, we only see the past. The closer an object is, the fresher its image. The farther away, the older. This time lag, this built-in delay between reality and perception, is a feature of the universe itself. It is not a limitation of our instruments, it is the speed limit of information, and this speed limit is about to become more than an inconvenience. It is about to become the defining horror of cosmic scale. Now imagine something strange. Imagine that the sun suddenly, impossibly, doubled in brightness. You would not know immediately. The sun's light, travelling at the cosmic speed limit, would take those same 8 minutes to reach your eyes. Now imagine the same thing happening on Proxima Centauri, our nearest stellar neighbour. If Proxima flared dramatically right now, at this instant, no one on Earth would know for over 4 years. The light carrying that information has to crawl across 4¼ light years of vacuum. 4 years of waiting just to learn about the nearest star's behaviour, and Proxima is practically in our lap. It is the closest possible neighbour. Any star you can see with the naked eye is tens or hundreds or even thousands of times farther away than that. Some of the brightest stars in the night sky are showing you light that left before you were born. A few are showing you light that departed before the Roman Empire collapsed. You are looking at history, not the present. The night sky is a museum, not a window. I want you to sit with how uncomfortable that is. Your intuition says that when you look up, you see what is there. What is actually happening is that you see what was there at 1,000 different moments in the past, all arriving at your eye at the same instant. The constellation Orion is not a snapshot of Orion. It is a layered composite. Betelgeuse, one of the shoulders of Orion, is about 500 light-years away. The light you see from Betelgeuse tonight left the star around the time Columbus was sailing the Atlantic. Rigel, the bright blue foot of Orion, is about 860 light-years away. Its light left before the Magna Carta was signed. These two stars appear side by side, yet their images are separated by centuries of history. The sky is not a place. The sky is a timeline, pretending to be a place. This is what I mean when I say your ruler bends. The tools you use to measure the pea in your hand and the room around you are not merely inadequate for cosmic distances, they are actively misleading. They tell you that stars are close, that the sky is a ceiling, that distance is something you could, in principle, cross. Distance in space is not like that. Distance in space is so vast that even light, the thing that makes seeing possible, becomes a slow messenger, and we are still only at the level of our own stellar backyard. The level where the sun is our clock, the planets are our landmarks, and Voyager is our flag planted at the edge. Everything we have discussed so far is, as I said at the start, about to vanish. Let me give you one final image to carry with you before we step outward. The sun, at full brightness, outputs a staggering amount of energy, about 3.8 times 10 to the 26th watts. That number means almost nothing to a human brain, so let me translate. The sun produces more energy in 1 second than humanity has used in all of recorded history combined. Every light bulb, every engine, every power plant, every nuclear reactor, every campfire, from the invention of fire to this very moment, less than 1 second of solar output. The sun is a furnace beyond anything our species has ever built or even imagined building, and the sun is one ordinary star, an average yellow dwarf, entirely unremarkable in its class. Now here is the punchline, the thing I want you to hold in your mind as we climb. All of that energy, all of that gravity, the entire nuclear might of our local star, is only enough to hold together a system whose gravitational reach extends, at its absolute outer edge, perhaps 2 light-years outward from the sun. 2 light-years. That is the sun's entire sphere of influence, the boundary where its gravitational authority finally loses out to the pull of other stars. 2 light-years, including the hypothetical outer Oort cloud, represents everything the sun owns, everything it controls. And 2 light-years at the scale we have been building is a tiny bubble in a universe where the distances we are about to encounter are not measured in light-years but in thousands of light-years, and then millions, and then billions, and then tens of billions. Each new layer is not merely larger, each new layer is larger by factors that make the previous one look like a rounding error. If the solar system is a small town, then the galaxy is an entire continent. But the continent is not the end. The continent is a single grain of sand on a beach we have not even begun to see. Each jump erases the previous scale from the map, and this is the pattern we will see repeat again and again for the rest of this journey. Every time you think you have reached the top, you will find that the top was the floor of the next room. Every time you think you have grasped the scale will laugh and grow. The universe is not merely big. The universe is structured in a way that your brain is not equipped to hold, and the first casualty of that structure is the ruler you were born with. Let me give you one last demonstration before we step outward. Think about how long it would take to count to 1 million. If you counted 1 number per second without stopping, no sleep, no food, no breaks, it would take you 11.5 days. Now think about counting to 1 billion. At the same rate, 1 number per second, it would take you almost 32 years. 32 years, just to reach 1 billion. A human lifetime, spent entirely on counting, barely crosses 2 billion. And in what comes next, we will be talking about 400 billion star. 400 billion. If you started counting the stars in our galaxy alone, 1 per second, without a single pause, you would need over 12,000 years to finish. Longer than recorded human history. Every civilization that has ever existed, counting in series, handing the task from one generation to the next, would still not be done. And that is just one galaxy. One galaxy out of 2 trillion. That is what is coming. The solar system, as vast as it feels, as impossible as Voyager's journey is, as humbling as the distance to the nearest star seems, is a single lit campfire at the edge of a stellar city. And the city is waiting. The city contains so many campfires that the campfires themselves become indistinguishable, blurring together into a river of light we call the Milky Way. Every point of light in that river, every dot of every constellation you have ever named, every star you have ever wished on, is another sun, with another beach ball, and another possible football field of planets and moons and comets. Hundreds of billions of them. And we are about to step back far enough to see them all at once. When we do, the football field you just walked, the one that held our entire solar system, will disappear. Not shrink, disappear. The closest star is already so far away that our scale model of the solar system, the one where the sun is a beach ball and Earth is a pea, requires us to place the next beach ball on the opposite side of the planet, and there are 400 billion beach balls waiting. Leave the football field behind, walk out of the stadium, close the door on the pea and the beach ball and the grapefruit and the mile of empty asphalt between Neptune and everything else. That entire model, The one that took you nearly 230 feet to walk across was only useful inside one solar system. The moment you try to use it to describe a galaxy, it collapses. Because the next step up is not another football field. The next step up is a step so wide that the football field with everything in it becomes invisible before you finish taking it. Let me show you what I mean. The solar system, from the Sun to roughly the outer Oort cloud, is about 2 light-years across. That is our stellar backyard, the full extent of the Sun's gravitational empire. Now zoom out. The Milky Way, the galaxy we live inside, is somewhere between 100,000 and 200,000 light-years across, depending on how you define the edge. Let me use a conservative middle figure. Let us say 100,000 light-years, the number that appears on most astronomy diagrams, while noting that recent studies using stellar streams and dark matter halo measurements suggest the true extent is closer to 200,000 light-years and possibly more. Even using the smaller figure, you already have a problem. The ratio between the solar system and the galaxy is roughly 1 to 50,000. If you tried to draw the Milky Way on a sheet of paper so that the entire galaxy fit on a single page, the entire solar system would be smaller than a single atom on that page. Not a speck, not a dot, an atom. Something you could not resolve with a household microscope, and that atom would contain everything we just discussed. The Sun, the planets, Voyager's 50-year journey, the Oort cloud, the 4¼ light-year gap to Proxima Centauri, all compressed into a region smaller than a pinprick. This is the first brutal truth about galactic scale. The solar system does not shrink on a galactic map. It disappears, and everything human civilization has ever thought about as space disappears with it. Try to hold that in your head. The pea in your hand, the beach ball at the end of the field, the grapefruit a quarter mile away, the fact that your fastest spacecraft has crawled only 15 billion miles in 50 years, all of it gone. Not diminished, gone. The map of the galaxy has no room to show you the thing you call home. That is the first sign your ruler is broken beyond repair. Now, let me try a different approach, because one scale model will not be enough to carry you the rest of this journey. Let us use time instead of distance. Imagine you are a beam of light, the fastest thing the universe allows. You have already seen how long light takes to move inside our solar system. 8 minutes to reach Earth from the Sun. Roughly 5½ hours to reach Pluto at an average distance. About a year to reach the outer Oort cloud. Already, light is slow at these scales. Now ask light to cross the Milky Way. Light, at 300,000 kilometers per second, needs approximately 100,000 years to travel from one edge of our galaxy to the other. Say that number slowly. 100,000 years. Longer than the entire existence of anatomically modern humans. When a photon left the far side of the galaxy and began its journey toward our position, our species had not yet invented language. We were scattered hunter-gatherer bands somewhere in Africa, still thousands of generations away from figuring out how to farm. The photon travelled, uninterrupted, through the void for the entire span of human history, watching nothing. It crossed the birth and fall of every empire we have ever built without slowing down, without being observed, without anything in its path. It is only now, tonight, arriving at the telescopes we finally built to catch it. That is how slow the fastest thing in the universe is at the scale of a single galaxy, and 100,000 years is the conservative estimate. More recent measurements using the orbits of dwarf satellite galaxies and the extent of stellar streams around the Milky Way suggest our galaxy may be closer to 200,000 light-years wide when you include the diffuse outer regions and the dark matter halo. Some estimates push that to 250,000, and a handful of researchers argue the true gravitational reach extends even further. Every new instrument, every new survey, every new measurement keeps making the galaxy bigger than the textbooks say. And remember, this is just the disk. This is just the part where stars actually live. The dark matter halo surrounding the galaxy, invisible and undetectable except through its gravity, extends much farther still, dominating the total mass of the entire system. We do not live in the galaxy. We live in the lit part of the galaxy, a thin, glowing layer on top of something vastly larger that we cannot see. Now let me try marching. Instead of light, let me put you on foot again, because walking is something your body understands. At a steady pace of 3 miles per hour, how long would it take you to walk across the Milky Way? The answer is so absurd that I want to warn you before I say it. If you could somehow walk at the speed of light, it would take you 100,000 years, as we just established. But you cannot walk at the speed of light. You walk at something like 220 million times slower than light, which means walking the Milky Way would take you somewhere on the order of 22 trillion years. That number, 22 trillion, is about 1,600 times longer than the current age of the universe. You could walk for the entire age of the cosmos, and then again and again, more than 1,000 times in sequence, and still not finish crossing the Milky Way on foot. The galaxy is that wide. Your body is that slow. The gap between the two is not a gap. It is a canyon so deep that human time disappears into it. Give up walking. Give up driving. Give up any vehicle humans have built, are building, or can theoretically imagine building. Even the fastest spacecraft we have ever launched, Voyager, would need over 1,700,000,000 years to cross just the disk of our galaxy. And that is assuming it could travel in a straight line without hitting anything. 1.7 billion years. To put that in perspective, the dinosaurs went extinct roughly 66 million years ago. Voyager, if launched the day the asteroid hit, would have covered less than 4% of the galactic disk by now, and our real Voyager has only been flying for 50 years. This is the first major emotional collapse of galactic scale. The gap between the stars is not merely empty. The gap is so vast that even theoretical future technology, travelling at speeds we do not yet know how to reach, would take lifetimes of civilizations to bridge it. And that is just from one star to the next. The galaxy is full of stars, not dozens, not millions, not billions, 400 billion, give or take. The exact number is debated because we cannot count them all, but 400 billion is the middle estimate. Some researchers argue it could be as high as 700 billion, depending on how many tiny red dwarfs and dim brown dwarfs hide in the galactic halo. Others say as low as 200 billion. The uncertainty itself is instructive. Our galaxy contains so many stars that we cannot count them within a factor of 3. We simply do not have instruments sensitive enough to distinguish 400 billion from 700 billion. Let me translate 400 billion into something your brain can touch. Earlier, I told you that counting to 1 billion, one number per second without stopping, would take about 32 years. To count to 400 billion at that same rate, you would need approximately 12,700 years. 12,700 years of unbroken counting. That is longer than the history of agriculture. That is longer than the entire span of recorded human civilization. If the first person ever to plant a crop had started counting stars at the moment they scattered the first seeds, and every generation since had passed the counting to the next, one number per second without a pause, we would still not be finished today. We would still have thousands of years of counting left, and at the end of all that effort we would have counted the stars in one galaxy. One galaxy. And we have not yet talked about the fact that our galaxy is not even the biggest one in our local neighbourhood. Now let me put the galaxy on a map you can visualize. Picture a flat disk, roughly shaped like 2 fried eggs stuck together back to back. In the center, a bulge of older stars clustered around a supermassive black hole called Sagittarius A star, an object we will return to in a moment. In the center, a bulge of older stars clustered around a supermassive black hole called Sagittarius A star, an object we will return to in a moment. It sits at the gravitational center, a deep well in the fabric of space, around which the entire galaxy rotates. Spiraling outward from the bulge, 4 major arms wind through the disk. Spiraling outward from the bulge, 4 major arms wind through the disk. Our sun, our beach ball, lives on a minor spur between two of those arms, about 26,000 light-years from the center. That means the light from the galactic core took 26,000 years to reach us. When you look toward the constellation Sagittarius and see that dense river of stars cutting across the Milky Way, you are seeing photons that left home thousands of years before the caves of Lascaux were ever painted. Let me describe the center of our galaxy in more detail, because what sits there is worth knowing. The Milky Way is not a pure spiral. It is a barred spiral, meaning that instead of a round bulge at the center, our galaxy has an elongated bar of stars crossing through the core, roughly 27,000 light-years long from tip to tip, rotating as a single coherent structure. The spiral arms do not emerge from a central point. They emerge from the ends of the bar. This was only confirmed in the 1990s and 2000s through infrared surveys that could see through the dust blocking our view of the galactic interior. Before that, we did not even know the shape of our own home with certainty. We had been living inside the Milky Way for the entire existence of our species, and still had not figured out its basic architecture until the last few decades. At the exact center of that bar, at the gravitational heart of the galaxy, sits Sagittarius A star, the supermassive black hole that anchors the entire spiral. Sagittarius A star contains the mass of about 4.3 million suns, compressed into a region whose event horizon would fit comfortably inside the orbit of Mercury. In 2022, the Event Horizon Telescope collaboration released the first direct image of it, a glowing orange ring surrounding a central shadow, confirmed through years of coordinated observations from radio telescopes across the entire Earth, combined into a single virtual instrument the size of the planet. Stars near Sagittarius, a star orbit, at extraordinary speeds. One star, S4716, completes an orbit around the black hole every 4 Earth years, reaching velocities of around 8,000 kilometers per second at its closest approach. That is nearly 3% of the speed of light, achieved by a star simply falling around the central mass. And the galaxy itself is not passive, it is actively eating. Right now, as I speak, the Milky Way is in the process of tearing apart the Sagittarius dwarf galaxy, stretching its stars into long streams that wrap around our disk like ribbons. Other small satellites are being slowly consumed as well. We have already absorbed many others. In 2018, researchers using Gaia data identified the remnants of a galaxy called Gaia Enceladus, which collided with and was consumed by the Milky Way roughly 10 billion years ago. Billions of its stars are still here, orbiting the galactic center on distinctive paths that give their foreign origin away. Our galaxy is not just a structure, our galaxy is a predator. It grew to its current size by devouring its neighbors, and it is still doing so today. Our sun orbits the center of this disk at a speed of about 140 miles per second. That is fast by human standards. Faster than any bullet, faster than any rocket. It is fast enough that in the time it takes you to hear this sentence, the Earth, along with the entire solar system, has traveled roughly 1,000 miles along its orbital path through the galaxy. And yet, at that speed, it takes the Sun about 230 million years to complete a single circuit around the galactic center. 230 million years for one orbit. The last time the Sun was in this exact position in the galaxy, dinosaurs were only just beginning to appear on Earth. The continents were arranged into a single supercontinent called Pangaea. When the Sun returns to where it is right now, assuming it survives that long, there may be nothing recognizable on Earth at all. A single galactic year is so long that entire evolutionary eras unfold within it. This rotation is also happening to everything we see. The Milky Way is not a static diagram, it is spinning. The arms are moving. Stars are passing each other at tremendous speeds. On the timescale of galactic rotation, nothing is still. But on human timescales, the sky looks frozen, because the galaxy is so vast that our motion across it barely registers from generation to generation. The stars look the same to you as they looked to the Greeks 2,000 years ago. not because they are not moving, but because they are moving in circles so huge that 2,000 years is nothing on the dial. Now let me introduce an analogy I want you to hold on to, because it will matter later. If you took the entire Milky Way and shrank it down until the Sun was the size of a single red blood cell, the galaxy at that scale would be about the size of the continental United States. A red blood cell spinning somewhere between the Rocky Mountains and the Mississippi River, surrounded by 400 billion other red blood cells, with vast empty space between every single one. You could put the whole solar system inside that red blood cell. You could put every ambition humanity has ever had, every planet we have ever dreamed of colonizing, every signal we have ever beamed into space, inside that single cell. And the cell would drift, nearly motionless from your zoomed-out perspective, through a country-sized structure so sparse that almost every direction you look is darkness broken by tiny specks of light. That is the galaxy. The stars are not crowded. They are lonely. The average distance between neighbouring stars in our part of the galaxy is about 4 light years. Recall how far that was. Now imagine that every direction you turn, the nearest light is 4 light years away, and the one after that is another 4 light years beyond, and the pattern continues for 100,000 light years in every direction along the disk. Most of the galaxy is not stars. Most of the galaxy is gap between stars. Matter is the exception. Void is the rule. Even inside the lit region of our galactic home, we are already swimming through almost perfect emptiness, peppered with occasional fires. And those fires themselves are not all the same. The Sun is an ordinary yellow dwarf, but in the galactic population, ordinary is actually the exception. Most stars in the Milky Way are small red dwarfs, cool and dim and long-lived, burning so slowly that they can last trillions of years. These red dwarfs outnumber Sun-like stars by nearly 10 to 1. There are also giant blue stars, hundreds of times more luminous than the Sun, but burning through their fuel in just a few million years before exploding as supernovae. There are ancient red giants in their death throes, swelling until they would swallow the inner planets if they were our Sun. There are white dwarfs, the collapsed cores of dead stars, each packing the mass of a sun into a sphere the size of Earth. There are neutron stars, the even denser remnants of stellar explosions, where a teaspoon of material would weigh as much as a mountain. There are black holes, invisible gravitational holes in the fabric of space, scattered throughout the galactic disk in numbers we are still trying to estimate. Some models suggest there are 100 million stellar mass black holes drifting through the Milky Way, each one a dead star that once shone, before collapsing into a point of such extreme gravity that not even light can escape it. 100 million black holes in one galaxy, hidden, silent, passing through the darkness between the fires. And remember, all of this, every star and dwarf and giant and black hole, sits inside a cocoon of dark matter that outweighs the visible galaxy by a factor of roughly 10. Dark matter is the invisible substance that provides most of the gravitational pull holding galaxies together. We know it exists because without it, the outer stars of the Milky Way would fling outward into intergalactic space. The visible galaxy alone does not have enough mass to hold itself together at observed rotation speeds. Something else, something we cannot see, is doing most of the gravitational work. That something else forms a roughly spherical halo extending far beyond the bright disk, outweighing the stars and gas of our galaxy by roughly a factor of 10. The total mass of the Milky Way, including this dark matter halo, is estimated at around 1.5 trillion times the mass of the Sun. Some recent studies using the motions of satellite galaxies and stellar streams suggest the figure could be even higher, perhaps 2 or 3 trillion solar masses, though these estimates remain debated. Whatever the exact number, the clear fact is that the luminous galaxy we see is only 1/10 of what is actually there. 9/10 of the Milky Way is invisible. We live in a dark structure faintly decorated with stars. Let me try one more way to convey the sheer dimensional enormity of our galaxy. Imagine every grain of sand on every beach on Earth, Scientists have estimated that number to be roughly 7,500 quadrillion grains, a ridiculous number. Now forget the whole Earth and focus on just one ordinary-sized beach. A beach of a few miles of shoreline contains something on the order of 10 quintillion grains of sand in total, depending on how you count, maybe more. Now imagine that every grain on that beach represents one star in the Milky Way. 400 billion grains. That is only a small handful of sand, maybe enough to fill a coffee cup of stars. That is our galaxy. It sounds small when expressed that way, because a coffee cup is something your hand can hold. But remember, each grain is a star. Each star is a furnace like the sun. Each furnace is surrounded by its own possible planetary system, and the distances between the grains are measured in trillions of miles. The coffee cup has been stretched out across 100,000 light years. The grains have been scattered through a volume so large that even at light speed, you could never visit more than a tiny fraction of them in the age of the universe. Every one of those 400 billion suns might have planets. In fact, we now know, based on decades of exoplanet surveys, that planets are the rule rather than the exception. Nearly every star in the galaxy has at least one planet, and most have several. Conservatively, the Milky Way contains at least 1 trillion planets. Some estimates push that figure higher. 1 trillion worlds. Rocky worlds, gas giants, ice worlds, desert worlds, ocean worlds. Worlds with atmospheres nothing like our own. Worlds where the chemistry of life could be radically different from anything Earth has produced. Among those trillion planets, some fraction lie in the habitable zone of their star, where liquid water could exist on the surface. Estimates suggest billions of potentially Earth-like worlds in our galaxy alone. Billions. In one galaxy, out of 2 trillion. We will get to the 2 trillion in the next part. For now, hold the galaxy in your mind. Hold the disk, the arms, the central black hole, the 400 billion stars, the trillion planets, the 100 million hidden black holes, the dark matter halo, the 100,000-year light crossing time, the 12,700 years of counting, the coffee cup of grains stretched across an entire continent worth of space. Hold all of it. This is the Milky Way. This is our home. And now, here is the hinge. The moment that shatters the idea that the galaxy is the end of the journey. Point your telescope toward the constellation Andromeda on any dark autumn night. You will see a faint smudge of light, barely visible to the naked eye, that looks like nothing more than a small cloud. That smudge is not a cloud. That smudge is another entire galaxy, comparable in size to ours, possibly larger, containing roughly 1 trillion stars. The Andromeda Galaxy. And it is 2.5 million light-years away. Let me explain what that means. The light you see from Andromeda tonight left that galaxy 2.5 million years ago. 2.5 million years. The entire species of Homo sapiens is only about 300,000 years old, so the light reaching your eyes from Andromeda has been travelling for 8 times longer than our species has existed. When those photons began their journey, our ancestors were not yet human. They were early hominids, maybe Homo habilis, wandering the grasslands with stone tools, with no idea that the smudge they could not yet even conceive of existed at all. The photons crossed the void while our entire genus rose and branched and evolved, and they arrived, just now, in your eye. Here is the thing that should really sink in. Andromeda is our closest major galactic neighbour. 2.5 million light-years is the nearest, not the typical. It is the galaxy in our own local group, the one right next door on a cosmic scale, and even this closest neighbour is so far away that light from it takes 8 times longer to reach us than our species has existed. The gap between galaxies, even among close neighbours, dwarfs the gap within galaxies by such enormous factors that the galaxy itself, which seemed infinite a few paragraphs ago, becomes a tiny island surrounded by oceans of darkness. The Milky Way is huge, but the Milky Way is one of at least 2 trillion galaxies. And the space between galaxies is so empty that if our sun were a beach ball again, the nearest galaxy's nearest star would be on another planet, not another country. Actually, it is even stranger than that. The Andromeda Galaxy is moving toward us, right now. As I speak, Andromeda is racing through intergalactic space at roughly 110 kilometers per second, aimed directly at the Milky Way. Gravity is pulling the two giants together. In about 4.5 billion years, according to the standard calculation, Andromeda should reach us, though recent analyses in 2024 suggest the timing and even the certainty of the collision are less settled than once thought. If the merger does occur, the two galaxies will collide and begin to combine. Not crash, merge. The stars are so far apart within each galaxy that almost none will physically hit each other. Instead, the gravitational fields will interweave, the spiral arms will distort, and over hundreds of millions of years of cosmic dance, the two disks will fold together and eventually settle into a single giant elliptical galaxy. Astronomers have already coined names for this hypothetical future galaxy: Milkomeda, or Milkdromeda, depending on who you ask. Should it come into being, it would be the largest structure in the local group, a merged titan containing more than 1 trillion stars. And here is the detail that ties everything to what comes next. Milkomeda, even after the merger, will still be tiny. The merger of two of the largest galaxies in our local neighborhood will not produce anything that matters on the next scale up. We have not yet reached the next scale up. We have only just noticed that there is more than one galaxy. Andromeda is the first step, not the last. The local group contains at least 80 galaxies, most of them small dwarfs orbiting the two giants. Beyond the local group lies something larger. Beyond that, something larger still. The ladder keeps climbing, and we are about to climb it. The galaxy, this 100,000 light-year wonder containing 400 billion stars and 1 trillion planets, and enough mysteries to occupy human science for the next 1,000 years, is about to be revealed as a single grain in a structure so vast that the galaxy itself, like the solar system before it, will vanish from the map. You thought the solar system was the story? It was not. You thought the galaxy was the story? It is not. The galaxy is a colossal island, yes, but the ocean is already waiting, and the ocean has its own islands, and the islands are grouped into archipelagos, and the archipelagos are woven into continents of galaxies we have not yet named. And somewhere out there, rushing silently through the dark, Andromeda is already closing the distance. Step back from the galaxy. Not another few light years, not another 1,000. Step back far enough that the entire Milky Way, the whole spiral wonder of 400 billion stars we just spent so long building in your mind, shrinks to a single point of light. A dot. One dot. That is how you have to picture it now, because what we are about to describe is a structure so large that individual galaxies are no longer the subject. Individual galaxies are pixels. The picture is made of millions of them. Before we zoom all the way out, though, we need to take the next step, because right next to our galactic dot sits another dot, and then another, and then another. The Milky Way does not drift alone through intergalactic space. It is part of a small, gravitationally interacting cluster of galaxies called the local group. The local group contains somewhere between 80 and 100 known galaxies, although the vast majority of them are dim dwarfs that we only discovered in the last few decades by deep surveys. The two dominant members are the Milky Way and Andromeda, the future merger partners. A distant third is the Triangulum Galaxy, a smaller spiral containing around 40 billion stars, considerably less massive than our Milky Way. Everything else in the local group is a satellite, a scrap, a leftover. Our galaxy alone has dozens of dwarf satellites. Andromeda has even more. Most contain only a few billion stars or fewer, and some are so faint and diffuse that we can barely detect them against the background sky. The local group spans about 10 million light-years across. Let me hold that number for a moment. As we established, The Milky Way is roughly 100,000 light-years wide. The local group, therefore, is about 100 times wider than our galaxy. If the Milky Way were a single dinner plate on a table, the local group would be a region about 3 meters across, with Andromeda being a second dinner plate on the far side, Triangulum a side plate somewhere between them, and the rest of the local group sprinkled as dust motes and crumbs across the whole tablecloth. Mostly empty table, occasional plates, lots of dust. And 10 million light-years is already a distance that breaks the ruler you were just getting used to. Light, our messenger, needs 10 million years to cross from one end of the local group to the other. The Milky Way and Andromeda are separated by 2.5 million light-years, but other members of the local group lie much farther out, drifting at the edges of the gravitational well, barely held in place. Some of them are slowly falling inward, on orbits that will eventually bring them into collision with one of the two giants. Others are on the edge of escape, dragged along by cosmic expansion, destined to drift away into the void. The local group is not fixed. It is a slow-motion gravitational dance, playing out over billions of years. But here is the part that matters for scale. The local group, for all its size, is one of the smallest structures at this level of organization. Most galaxies in the universe belong to much larger groups, and groups in turn belong to even larger structures called clusters. A galaxy cluster is a collection of hundreds to thousands of galaxies, all gravitationally bound, all swirling through each other in complex orbital patterns across millions of light-years of space. The nearest major cluster to us is the Virgo cluster, located about 54 million light-years away. Virgo contains somewhere between 1,000 and 2,000 galaxies, packed into a volume spanning roughly 15 million light-years. It is gigantic by every standard we have used so far, and it is the closest cluster to us. Beyond Virgo lie other clusters, larger and more massive, stretching in every direction for as far as our telescopes can see. At this scale, we also need to introduce something new, something that did not matter at the level of single galaxies, but becomes essential now. The space between galaxies in a cluster is not true vacuum. It is filled with extremely hot, diffuse gas at temperatures of tens of millions of degrees. This intra-cluster medium glows in X-rays and, astonishingly, contains more mass in hot plasma than all the visible stars of all the cluster galaxies combined. A galaxy cluster is not just a bunch of galaxies, it is a hot glowing cauldron of gas with galaxies embedded in it like croutons in a bowl of soup. And the cauldron itself is held together by dark matter, which outweighs the hot gas and the stars combined by a factor of several. Most of a cluster's mass, by far, is invisible. The glowing galaxies are decoration, the glowing gas is a side dish. The main course is dark. Think about what that actually means, because it is stranger than it sounds. When you look at an image of a galaxy cluster, what you see are the galaxies. Bright spirals and fuzzy ellipticals scattered across a black background. That image is a lie of omission. The black background is not black. The black background is a bath of superheated plasma at temperatures between 10 million and 100 million degrees, stretching across millions of light-years between the galaxies. This plasma is so hot that its atoms have lost most of their electrons. It glows in X-rays, invisible to the human eye, but unmistakable to space telescopes like Chandra and XMM Newton. And it contains more mass than every star in every galaxy of the cluster combined. A typical rich cluster has something like 10 times more mass in hot gas than in visible stars, and several times more mass again in dark matter beyond that. The galaxies are the smallest component. The hot gas is the middle component. The dark matter is the dominant component. When you look at a cluster, you are looking at the smallest, faintest layer of a multi-layered structure, and you are seeing it against a cosmic glow that your eyes cannot detect and your body would be instantly vaporized by if it could. The clusters are not cities of galaxies floating in vacuum. The clusters are hot, structured, gravitationally active environments where gas flows between galaxies, where supermassive black holes in the central galaxies pump energy into the surroundings. where the temperature of empty space is measured in millions of kelvins. Our quiet image of galaxies suspended in blackness is a human limitation, not the truth. Now zoom out further. The Virgo cluster and the local group are not isolated. They are connected by gravity and by streams of smaller galaxies and gas into something much larger. Astronomers once called this the Virgo Supercluster, a structure roughly 110 million light-years across. For decades, that was considered our cosmic address. In 2014, a team of researchers led by Brent Tully at the University of Hawaii used new techniques mapping the peculiar velocities of tens of thousands of galaxies and revealed that the Virgo supercluster is itself merely a lobe of something far larger. They named this larger structure Laniakea, a Hawaiian word meaning immense heaven. Laniakea spans approximately 520 million light-years across and contains roughly 100,000 galaxies. The Milky Way, for all our trouble, sits not near the center of Laniakea, but near its edge, on the outskirts of a gravitational basin that slopes inward toward a region called the Great Attractor. 100,000 galaxies. Let that land. Each of those galaxies contains, on average, 100 billion stars. If you multiplied out the full stellar count of Laniakea, you would get something around 10 quadrillion stars. 10 quadrillion. A number so large that if you wrote it in full, it would be 1 followed by 16 zeros. 10,000 trillion stars in one supercluster, our supercluster. And Laniakea is not especially large among superclusters. Before we go further, I want to make something clear, because it is the single most important conceptual shift in what follows. At every previous scale, we were describing objects. A planet is an object. A solar system is a collection of objects. A galaxy is a much larger collection of objects. Even the local group behaves somewhat like an object, gravitationally bound to itself. But at the scale of superclusters and beyond, we stop describing objects altogether. We start describing architecture. The universe, at its largest scales, is not built out of things. It is built out of patterns, specifically a vast, filamentary, foam-like pattern called the cosmic web. Imagine you could see the universe in 3 dimensions, not as a black sky dotted with stars, but as a map of all its matter stretched across billions of light-years. What you would see would not look random. You would see something that looks disturbingly like the neurons of a brain, or the delicate structure of a soap foam, or the root network of a vast tree. Long, thin filaments of galaxies stretch between dense knots where galaxies pile up into clusters. Between these filaments yawn enormous bubbles of almost perfect emptiness. The filaments form sheets, the sheets form walls, and the walls enclose bubble-shaped voids that dwarf any structure we have discussed so far. This pattern, this foam, is the cosmic web. It is the true shape of everything. Let me try to describe how you get one. Right after the Big Bang, the universe was extraordinarily smooth, but not perfectly so. There were tiny quantum fluctuations, stretched to cosmic size by a process called inflation, which left faint patterns of higher and lower density throughout the early cosmos. Those patterns are recorded in the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the entire sky. Every place where density was slightly higher than average attracted more matter through gravity. Every place where density was slightly lower lost matter to its neighbours. Over hundreds of millions of years, these tiny differences amplified dramatically. Dense regions got denser, empty regions got emptier. Gravity turned ripples into rivers, and rivers into architecture. To understand how astonishing this is, think about what the early universe actually looked like. For the first few 100,000 years after the Big Bang, the cosmos was an almost perfectly uniform fog of hot plasma. Protons, electrons, and photons, all mixed together at temperatures of thousands of degrees, with density variations of only about 1 part in 100,000. That is the level of smoothness we are talking about. If you measured the density of the early universe at any 2 points separated by enormous distances, the numbers would agree to 5 decimal places. This was as close to featureless as a physical system can get while still being a physical system. And yet, hidden inside that near-perfect smoothness, written into the fabric at the level of the 5th decimal place, were the seeds of everything we have been describing. Every galaxy, every cluster, every supercluster, every filament and wall and void, every star and every planet and every living creature was encoded in those tiny density ripples that rose and fell below the surface like whispers in a quiet room. Gravity did the rest. Over the following 13.8 billion years, gravity amplified those whispers into the cosmic web. The near-uniform fog became the architecture of the entire visible universe. That is not a metaphor. That is the actual scientific account of how the structure we see today came into existence. Structure was not placed. Structure was grown, from fluctuations smaller than a breath, into filaments billions of light years long. And the thing that did most of the growing was not the matter we see, it was dark matter. Dark matter is a form of mass that does not interact with light, cannot emit, cannot absorb, cannot reflect, and cannot be touched by any of the senses or instruments that rely on the electromagnetic spectrum. It exists only through its gravity. We know it is there because galaxies rotate faster than their visible mass can explain, because galaxy clusters hold together despite their members moving too quickly to be gravitationally bound by stars alone, because light from distant objects bends around invisible mass we cannot see directly. Across the cosmos as a whole, dark matter outweighs normal matter by a factor of about 5 to 1. And dark matter, not normal matter, is what actually built the cosmic web. The dark matter collapsed first, forming invisible filaments and halos. Then, over hundreds of millions of years, normal matter, hydrogen and helium gas, flowed into those dark valleys and lit up as stars. Every galaxy you see is embedded inside a dark matter halo, many times larger than its luminous region. Every filament you map is a dark matter filament, decorated with visible galaxies like streetlights along an invisible road. The web itself, the true framework of reality, is almost entirely dark. What we see is the sparkle on the surface. The structure beneath is hidden, and it outweighs the sparkle by margins we are still refining. The end result, after 13.8 billion years of gravitational sculpting, is what we see today. Galaxies are not randomly scattered, they line up along the filaments. Clusters form where filaments cross. Superclusters are clusters of clusters of clusters, all tracing the invisible scaffolding of dark matter that makes up the bulk of the web. And the voids, the bubbles of emptiness between the filaments, are the dominant feature. By volume, voids account for something like 80% of the observable universe. 80% of everything, by volume, is nothing at all. No galaxies, no clusters, not even dust. Just dark matter sparsely filtering through almost perfect vacuum. Let me give you a sense of void scale by talking about one specific example. In 1981, an astronomer named Robert Kirshner discovered an enormous empty region in the direction of the constellation Boötes. At first no one believed him, because the region was simply too large to make sense. When they finally confirmed it, the Boötes void turned out to be a roughly spherical emptiness, approximately 330 million light-years across. 330 million. Inside a region of that volume, astronomers would normally expect to find several thousand galaxies, because that is how densely galaxies populate the cosmic web. On average, Boötes contains only about 60 galaxies, where there should be thousands. The emptiness is so extreme that if the Milky Way happened to sit at the center of the Boötes void, the ancients might never have noticed any other galaxies at all. Our closest neighbor would be so far away that early telescopes could not have detected it. We would have grown up thinking our single galaxy was the entire universe, because the rest of it would be too distant to see. And the Boötes void is not unique. It is one of many such supervoids scattered throughout the cosmic web. There is a local void right next to us that our galaxy is actively fleeing from at around 600,000 miles per hour, pushed by the gravitational outflow from its emptiness. There are other voids hundreds of millions of light years across, in every direction we can map. The cosmic web is mostly web by shape, and mostly void by volume. Every filament you see on a map of the universe is a thin river of galaxies winding through an ocean of nothing. Now let us climb the ladder of known superstructures, because the numbers are about to become absurd. Laniakea, as we said, is 520 million light-years across. It is our home supercluster, though the researchers who defined it noted that Laniakea is not truly gravitationally bound. Cosmic expansion is already, slowly, beginning to pull it apart. But Laniakea is not the biggest supercluster. In 2024, astronomers announced a newly recognized structure called the Einasto Supercluster, named after the pioneering Estonian astronomer Jaan Einasto. The Einasto Supercluster spans roughly 360 million light-years and contains tens of thousands of galaxies. It is in some respects more massive than Laniakea, containing a stellar census estimated at around 26 quadrillion stars. 26,000 trillion stars in a single supercluster, which is itself only one of many. Larger still is the Shapley Supercluster, which sits around 650 million light-years away. Shapley is one of the most massive concentrations of matter in our cosmic neighborhood, containing thousands of galaxies and pulling on the entire Laniakea region with its gravity. In fact, our whole supercluster is drifting toward Shapley at several hundred kilometers per second. Shapley, in turn, is part of even larger flows. Let me make this concrete. Our Milky Way, right now, is moving through space at about 600 kilometers per second, relative to the cosmic microwave background, the stationary reference frame of the universe as a whole. 600 kilometers per second. Every second, our entire galaxy, with all its stars and planets and worlds, travels a distance greater than the width of a small country. In a single day, it covers more than 50 million kilometers every second, and we are being pulled. Every second, and we are being pulled, not drifting randomly, pulled. In the 1970s, astronomers noticed that galaxies in our general region of space were all flowing coherently in the same direction toward a point in the direction of the Centaurus and Norma constellations. That is the great attractor mentioned earlier, an invisible gravitational concentration that could be detected by its pull long before anyone could see what was pulling. The great attractor lies roughly 150 million light-years away, inside the Laniakea Supercluster, and it turned out to be a dense concentration of galaxy clusters, partially obscured by the disk of our own Milky Way blocking the view. But the great attractor itself is not the real destination. The great attractor is being pulled towards something larger. The entire flow of our local corner of the universe, including the great attractor itself, is heading toward the Shapley Supercluster, a gravitational monster 650 million light-years away, containing the mass of at least 10,000 Milky Way-sized galaxies. We are falling. Laniakea is falling. The great attractor is falling. All of it is pouring across hundreds of millions of light-years toward Shapley, which itself may be falling towards something we have not yet mapped. The cosmic web is not static, it is flowing. Matter is constantly draining from voids into filaments, from filaments into clusters, from clusters into superclusters, from superclusters into even larger concentrations. We are passengers on a current we cannot feel, moving at hundreds of kilometers per second toward destinations we may never reach, because cosmic expansion may pull the destination away before we arrive. Now, let us jump to something discovered only last year. In February of 2025, a team led by astronomer Hans Boehringer published the first all-sky map of the largest structures in our relatively nearby universe, within a range of several hundred megaparsecs. They identified 5 enormous superstructures, and the largest of them they named Quipu, After the knotted chord recording system used by the ancient Inca to store numbers, Quipu is roughly 1.3 billion light-years long. 1.3 billion light-years, a structure so large that light, our universal messenger, needs a full 1,300,000,000 years to cross its length. That is nearly a tenth of the age of the universe, spent crossing a single structure. Quipu contains the mass of about 200 quadrillion suns, 200,000 trillion solar masses, and Quipu is only one of 5 similarly scaled superstructures recently mapped. Together, the 5 structures contain around 45% of the galaxy clusters in the local universe, about 30% of the galaxies, and roughly a quarter of all matter in our cosmic region. Quipu alone is so massive that it distorts the cosmic microwave background and warps measurements of how fast the universe is expanding. Let me slow down, because what I just said deserves its own moment. A single object in the universe is so large that it distorts our measurement of the universe itself. The gravitational pull of Quipu on the light passing through it, and on the galaxies embedded within it, is measurable enough to change the numbers we plug into our cosmological models. If you want to know how big the universe really is, and how fast it is expanding, you cannot ignore Quipu and its siblings. They are part of the measurement. The thing we are trying to measure has features inside it that are so massive they interfere with the measurement. This is the point where scientific instruments start bumping into scientific humility. We are no longer observing the universe from outside it. We are observing it from inside a structure that tilts our readings. Quipu is now the largest known structure in the relatively nearby universe, but there are candidate structures even larger, stretching further into cosmic distance and further back in time. The Sloan Great Wall, discovered in 2003, spans roughly 1.4 billion light-years. The Hercules Corona Borealis Great Wall, identified through the clustering of distant gamma-ray bursts, is estimated at around 10 billion light-years in length, though its coherence as a single structure remains debated among astronomers. If real as a single gravitationally linked object, the Hercules Corona Borealis Great Wall would be roughly a tenth of the diameter of the observable universe. Some studies argue it could be even larger than that. Other studies argue it is not truly a bound structure, but rather a statistical clustering of events. This debate is live and unresolved, and I want to flag it honestly. What we can say with confidence is that there are structures in the observable universe that stretch across many billions of light years, and that each new survey tends to push the maximum size upward rather than downward. To appreciate what this means, consider the following. Inflation, the theory of how the very early universe expanded, predicts that on sufficiently large scales, the universe should be smooth and uniform. This is called the cosmological principle. It is one of the foundational assumptions of modern physics. The principle states that if you zoom out far enough, the universe should look roughly the same everywhere, with no preferred direction and no gigantic lumps. According to standard models, no structure should be larger than about 1.2 billion light-years. Beyond that scale, the universe should be statistically smooth. But the Hercules Corona Borealis Great Wall appears to be almost 10 times too large for this limit. The Sloan Great Wall is borderline. Quipu is borderline. Every time we build a bigger telescope, we find something that is not supposed to exist. This is a live tension in cosmology. Either these structures are not truly coherent, and we are fooling ourselves by seeing patterns in random data, or the cosmological principle needs modification, or we do not yet understand how matter organizes on the largest scales. Astronomers and cosmologists continue to argue about this, and I am not going to resolve the argument in a single sentence. What I will say is this: even if we take only the structures that are confidently confirmed, the scales involved are beyond anything the human mind was ever designed to hold. Quipu, confirmed, mapped, named, and published, is already so large that light takes more than 1 billion years to cross it. Now zoom out one more step. Superclusters and superstructures like Laniakea, Shapley, and Quipu are themselves part of the larger cosmic web. The filaments connect them. The voids separate them. The web stretches in every direction, uniformly, filling the entire observable universe with the same foam-like pattern. There is no center, there is no edge, there is just web, and more web, and the bubbles of void between. Let me drive this home with one more comparison. If you took the entire Milky Way galaxy, the 100,000 light-year disk containing 400 billion stars that we spent so long building up, and placed it somewhere in the cosmic web, how much of the web would it occupy? The answer is almost none of it. If the cosmic web were the size of Earth, the Milky Way would be smaller than a speck of dust, not a grain of sand. A speck of dust, a thing you would brush off a shirt without noticing. The entire galaxy, the one that makes the solar system vanish, the one that takes 100,000 years for light to cross, is itself a dust mote on the scale of the web. And here is the point that makes this part of the story more than just numbers. At this scale, distance itself begins to behave strangely. Because the universe is expanding, the space between galaxies is growing. Galaxies that are not gravitationally bound to each other are drifting apart. Within the local group, we are bound. The Milky Way and Andromeda will merge. But beyond the local group, distances are increasing. Laniakea itself, our supercluster, is slowly being pulled apart by cosmic expansion. In the far future, our descendants, if any exist, will see fewer and fewer galaxies in the sky. The cosmic web will stretch, the filaments will thin, and the voids will grow. The structure we see today is not permanent. It is a phase. We are living inside the cosmic web at a particular moment of its evolution, and the web itself is slowly dissolving on timescales of tens of billions of years. The light we see from distant superclusters tonight shows us those structures as they existed hundreds of millions or billions of years ago. When we look at Quipu, we are looking at Quipu in the deep past. The Quipu that exists right now, in cosmic present time, has already evolved, already grown, already been touched by billions of years of expansion. We cannot see it as it is. We can only see it as it was. Every large-scale map we make of the universe is a map of history, not geography. The sky is a timeline, as we said earlier, but at cosmic scale the timeline is layered across billions of years simultaneously. You are looking at Andromeda as it was 2.5 million years ago, Virgo as it was 54 million years ago, Laniakea as it was hundreds of millions of years ago, Quipu as it was over 1 billion years ago, and the most distant structures we can detect as they were when the universe was only a fraction of its current age. Every direction you look, you are looking backward through time. And here is the thing to carry into the next part. All of this, every filament, every cluster, every supercluster, every wall and void and superstructure, every galaxy and every star and every planet we have ever catalogued, fits inside something called the observable universe, a vast region we will properly unpack in a moment. Inside that sphere, astronomers estimate there are roughly 2 trillion galaxies. 2 trillion. Each with its own stars, its own planets, its own possible civilizations, its own cosmic web filament to which it clings. 2 trillion is the count we will examine next, and I want you to hold it ready, because I am going to do something with it that no one tells you. For now, understand this. The cosmic web is the skeleton of reality. Galaxies are the fireflies sparkling on the skeleton. Stars are atoms inside the fireflies. Planets are parts of atoms. Human beings are infinitesimal events on a single planet. And even the skeleton itself, the web we can see, is only what the light has had time to show us. The structures you have just learned about, Laniakea and Shapley and Quipu and the Great Walls and the Voids, are mapped within a region we can actually observe. They are not the full inventory. They are the visible portion, the portion that exists within the cosmic light horizon. Every previous jump in this journey has been a jump within that horizon, from the solar system to the galaxy, from the galaxy to the local group, from the local group to the supercluster, from the supercluster to the cosmic web. Each of these jumps happened inside the same 93 billion light-year sphere we are about to examine. The sphere has been the container the entire time. Now, we are going to step outside the container, because here is the thing the name observable universe tries to warn you about. The observable universe is not the universe. It is only the portion from which light has had time to reach us in the 13.8 billion years since the Big Bang. Everything beyond that horizon is real and exists, but is forever invisible to us, and the universe beyond the horizon may be much larger than the universe inside it, possibly enormously larger, possibly infinite. That is the next step. That is where the ladder stops being a ladder and becomes something your mind cannot climb. Next, we will reach the boundary of what we can see, and then we will do the disturbing thing. We will look past it. The cosmic web you just learned about, the structure that makes the Milky Way a dust mote, is itself a dust mote on what comes next. And what comes next is not a bigger structure. What comes next is a horizon, a wall of light, beyond which the rules of observation stop applying, and the scale of existence becomes unknowable in the strictest sense of the word. The trap we have been falling into, step by step, finally reveals its flaw. There is no flaw. There is another room, and the door is already open. We have arrived at the sphere, the last container, the boundary around which every previous part of this journey has been nested. It is time to see it for what it is, and then, once we have seen it, to do the one thing the word observable has been warning us about since the beginning. Step past it, look at what we cannot see, and accept, finally, what that means. The observable universe is a sphere centered on you. Not on Earth, not on the Sun, not on the Milky Way, but on you, the observer. It has a radius of approximately 46.5 billion light-years in every direction. Its full diameter is therefore about 93 billion light-years. Inside that sphere lies every galaxy, every star, every planet, every supercluster and filament and void we have talked about. Inside that sphere, astronomers estimate there are roughly 2 trillion galaxies. Although recent studies using the James Webb Space Telescope have begun to suggest the true count may be somewhat lower, perhaps several hundred billion, once faint dwarfs are properly accounted for. Even using the more conservative estimates, the number of galaxies in the observable universe is so large that it exceeds by several orders of magnitude every star in our own galaxy. Every galaxy. More numerous than all the stars in the Milky Way. And every one of those galaxies contains, on average, hundreds of billions of stars of its own. The total stellar count of the observable universe runs into the range of 10 to the 23rd power, 100,000 billion stars, a number so large that you cannot meaningfully compare it to anything in human experience without the comparison itself becoming absurd. Let me try anyway, because the purpose of this final stretch is not to list numbers but to feel them. Astronomers sometimes point out that the observable universe contains more stars than grains of sand on every beach on Earth. That comparison has become famous, and it is true, but it has also been repeated so many times that it has lost its shock. So let me try a different approach. Forget the beaches. Instead, think about the total number of cells in your body. A human being contains roughly 30 trillion cells. Every neuron, every red blood cell, every skin cell, every gut bacterium, every one is a living machine of staggering complexity. 30 trillion. Now, the observable universe contains roughly 100 sextillion stars, which is more than 3 billion times the number of cells in your body. Every beating heart, every thought, every movement you have ever made depends on those 30 trillion cells, and the stars overhead outnumber them by margins that make the comparison itself collapse. There are more suns in the visible universe than seconds that have passed since the Big Bang, by enormous factors, and you are staggeringly complex. Your body is considered, by some scientific definitions, the most complicated object we know of, and the stars outnumber your cells by orders of magnitude. Hold that image. Every cell in your body, right now, is matched by several stars somewhere in the sky. Every thought in your head is matched by galaxies worth of suns, and all of them fit inside our sphere of 93 billion light years, which is itself, as we are about to see, only a fragment of what exists. Here is where we have to confront something uncomfortable. 93 billion light years is not the size of the universe. It is the size of the part we can see. The word observable is not decorative. It is a genuine, physical limit. Light has only had 13.8 billion years to travel since the Big Bang. Anything whose light has not yet reached us is, from our perspective, not merely unknown. It is unknowable in the strictest scientific sense. It is outside the horizon of causality. We can calculate that it must exist, based on the smoothness and consistency of what we do see, but we cannot observe it, cannot measure it, cannot ever receive any signal from it. It is real, but invisible. It is present but beyond reach, and the question then becomes, how much of it is there? No one knows. Let me repeat that, because it is the single most important sentence in this entire journey. No one knows how big the universe actually is. We know how big the observable portion is. We do not know how big the whole is. Estimates vary wildly. Some cosmological models suggest the true universe is at least 250 times larger in diameter than the observable universe. Others suggest the ratio could be vastly higher. Under inflationary cosmology, the leading theoretical framework for the early universe, the entire cosmos underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang, stretching quantum fluctuations to macroscopic scales and possibly pushing the full extent of spacetime to sizes that dwarf our observable sphere by factors so large they render the observable sphere 93 billion light-years wide and containing trillions of galaxies, essentially nothing. Possibly the universe is infinite, genuinely infinite, extending in every direction without end, containing infinite galaxies, infinite stars, infinite possibilities. We do not know, we may never know. And the reason we cannot know is that the speed of light, combined with the age of the universe, draws a wall around our observational capacity, and that wall does not move outward fast enough to catch up with cosmic expansion. Let me unpack what inflation actually implies, because it is the theoretical reason so many cosmologists expect the universe to be enormously larger than the observable part. In the first tiny fraction of a second after the Big Bang, something like 10 to the minus 36th of a second in, the universe underwent a burst of expansion so extreme that spatial distances doubled roughly every 10 to the minus 37th seconds. That is not a typo. Every fraction of a fraction of a fraction of a second, the distance between any 2 points doubled, then doubled again, then doubled again. By the time inflation ended, a region of space originally smaller than a proton had been stretched to a size larger than the entire observable universe we see today. And the process may not have been uniform. Inflation may have produced a cosmos whose full extent is larger than our observable sphere by a factor of 10 to the 26th, or 10 to the 56th, or larger still. Some versions of inflationary theory predict that inflation never fully ended, that it is still happening in distant regions of space-time, producing an ever-growing cosmos, of which our observable universe is one infinitesimally small bubble. In other versions, the universe is genuinely infinite, extending forever in every direction, containing infinite galaxies and infinite structure. These are not fringe ideas. They are mainstream cosmological models, supported by measurements of the cosmic microwave background, by observations of large-scale structure, by the flatness of space as measured across billions of light-years. The observable universe is not special. The observable universe is just the part we can see from this one vantage point at this one moment in cosmic history. Elsewhere, far beyond our horizon, there are more galaxies, more superclusters, more cosmic web, and in all probability, more observers, each sitting inside their own 93 billion light-year sphere, each looking out at their own 2 trillion galaxies, each unaware that we exist because the light from our region will never reach them, and theirs will never reach us. Let me explain that last point, because it is where the scale finally and completely collapses. The universe is not only big, the universe is expanding. Every galaxy outside our gravitationally bound local group is receding from us, and the rate of recession is proportional to distance. The farther away a galaxy is, the faster it moves away from us. At a certain distance, about 14 billion light-years, the recession speed reaches the speed of light itself. Beyond that distance, galaxies are receding faster than light. This does not violate Einstein's speed limit, because nothing is moving through space faster than light. It is space itself that is expanding, carrying galaxies along with it. And the upshot is that any galaxy beyond this cosmic event horizon is permanently out of causal contact with us. Signals sent from those galaxies now will never reach us. Signals we send now will never reach them. They exist, they are real, they may teem with civilizations, with art, with discovery, and we will never ever know anything about them. The wall is not merely informational, the wall is absolute. And there is a subtler problem, one that cosmologists have only recently begun to take seriously. Remember Quipu, the 1.3 billion light-year superstructure we discussed earlier? Its discoverers noted something unsettling in their published analysis. Quipu is so massive, and our location is so close to its gravitational influence, that it actually distorts our measurements of how fast the universe is expanding. The Hubble constant, the number that describes the rate of cosmic expansion, has been measured 2 different ways by 2 different kinds of observation, and the 2 measurements disagree by about 9%. This disagreement, known as the Hubble tension, is one of the largest unsolved puzzles in modern cosmology, and one of the leading explanations is that our local region of space, sitting inside or near these enormous superstructures, is not representative of the universe as a whole. The flow of galaxies towards Shapley, the gravitational tug of Quipu, the fact that we are embedded in a cosmic web rather than floating in average space, all of it may be tilting our readings of the universe itself. We are trying to measure the cosmos from inside a feature of the cosmos. The ruler is bent, and the bending may be invisible from our vantage point. This is not a small problem. It means that even the observable universe, the part we can in principle see, may be known to us only through measurements that are themselves distorted by the structure of the thing we are measuring. We are inside the map. We are inside the measurement. There is no outside perspective available to any human observer, now or ever. Even worse, this wall is closing in. Dark energy, the mysterious force accelerating cosmic expansion, is making the recession faster over time. Every year, galaxies that are currently just inside our cosmic event horizon slip beyond it, crossing permanently into the unreachable dark. In about 100 billion years, every galaxy outside the local group will have receded so far that their light will no longer be able to reach us. Future astronomers, whether living in our own descendant galaxy or in a merged system that may eventually form, will look up at a night sky empty of other galaxies. They will see their own stars and nothing else. They will have no evidence that the cosmic web ever existed, no way to measure the expansion of the universe, no cosmic microwave background remaining visible, no hint of the Big Bang at all. They will conclude, reasonably, from the evidence available to them, that the universe consists of a single galaxy in an empty void. They will be wrong, but they will have no way to know that. We are the lucky ones. We live in an epoch where the universe is still legible, where light from 2 trillion galaxies still arrives at our telescopes, where the cosmic microwave background still fills the sky with its 13.8 billion-year-old glow, where the scale of the cosmos is, for this moment in history, at its maximum knowable extent. Every generation before us saw less, because their telescopes were smaller. Every generation after us will see less, because expansion will have carried away more. We are at the peak of cosmic visibility, and the peak is already declining. This is the point in the journey where the emotions land. Not before, not in the middle, here, at the end. Because only now, standing at the edge of the sphere with the full weight of the ladder behind us, can the reflection be honest rather than decorative. We have not been building toward a punchline, we have been building toward an admission. The admission is this: every single time, on every single rung of the ladder we just climbed, we were thinking far too small. You thought your home planet was the world. Then you saw the Earth was a pea beside a beach ball, and the pea vanished. You thought the solar system was the scale of space. Then you saw the solar system disappear on the map of the galaxy, smaller than an atom on a galactic page. You thought the galaxy was everything. Then you saw the galaxy shrink to a dinner plate in a local group of plates, and then shrink further to a dust mote on the cosmic web. You thought the cosmic web was the skeleton of reality. Then you saw that the cosmic web is only the skeleton of the observable portion, and the portion may be a negligible fraction of the whole. At every step, the picture you had in your head before the step turned out to be radically, ridiculously, almost embarrassingly too small. And at no step did the correction simply involve multiplying by a reasonable factor. At every step, the correction was a leap of factors so enormous that the previous picture became not merely inadequate but essentially zero on the new scale. This is what the phrase, "and it is not even close," means. It does not mean the universe is bigger than we thought by a factor of 10. It means the universe is bigger than we thought by factors that make our first guess, and our second guess, and our third guess all equally irrelevant. Your intuition does not get closer to the truth by correcting it. Your intuition is replaced, erased, overwritten, and the thing that overwrites it is itself, at the next scale up, about to be overwritten. I want to sit with the emotional weight of this for a moment, because I think it matters. There is a tendency, when people learn about cosmic scale, to fall into one of two unhelpful reactions. The first is nihilism, the feeling that nothing matters because everything is small. I do not share this reaction, and I do not think the evidence supports it. The universe being large does not make your life small. The meaning of a thing is not a function of its size compared to other things. A thought inside your head is not less real because a galaxy is bigger than the thought. A love, a decision, a moment of beauty, a scientific insight, these do not scale with distance. They are their own thing. They happen once, here, and they are complete. The universe does not need to be small in order for your life to be meaningful. Those are separate questions. The second unhelpful reaction is mysticism. The feeling that cosmic scale reveals something spiritual or transcendent, that the universe's size means something beyond itself. I do not share this reaction either. The universe does not have a message for us. It is not speaking, it is not teaching, it simply is, and it is vast, and the vastness is a fact about its structure, not a communication. What I do think the vastness teaches, if teaching is even the right word, is something more narrow and more specific. It teaches intellectual humility. It teaches that the ruler you were born with is not the measure of reality. It teaches that whenever you feel certain you have grasped the scale of a thing, there is a very good chance the thing is still larger than your grasp. That is the real message of cosmic scale. Not that you are small, not that nothing matters, but that your first instinct, your second instinct, and your third instinct about the size of reality are, respectively, wrong, wrong, and still wrong. And the only appropriate response is a kind of quiet, clear-eyed awe. Now let me bring this all the way back to the beginning, because I want to show you how far we have travelled. We started with a hand in front of your face, a pea, a beach ball, a football field, a 230-foot walk from Earth to Sun, a solar system where the nearest star, at the same scale, sat on the opposite side of Earth. Then we left that scale behind, because the galaxy requires the solar system to vanish entirely. We walked the galaxy in time, at the speed of light, and the galaxy required 100,000 years of crossing. We counted its stars, and needed over 12,000 years of continuous counting to reach the total. Then we left the galaxy behind, because the local group shrunk galaxies to dinner plates on a tablecloth. We left the local group behind, because Laniakea reduced the local group to a lobe of something 500 million light-years across. We left Laniakea behind, because Quipu and the Hercules Corona Borealis Great Wall and the cosmic web stretched the map to billions of light-years. We left the cosmic web behind, because the observable universe contains the entire web and then some. And then, at last, we left the observable universe behind, because the observable universe is not the universe. The universe may be vastly larger, possibly infinite. Certainly, much of it is unreachable, receding from us at speeds that light itself cannot overcome. Every step made the previous step small. Every layer revealed the previous layer as a sliver, a fraction, a rounding error. And the pattern itself, is the thing worth remembering. The pattern is what the title was pointing at the whole time. The true scale of the universe is not just bigger than you think. It is bigger by structural, categorical, layer-on-layer factors that make the phrase "bigger than you think" a dramatic understatement. There is one more observation I want to leave you with before I let you go. It is subtle, and I have been holding it for the end because it could only land here. Consider what we have just done. You and I, two humans, descendants of small primates that evolved on the savannas of Africa a few 100,000 years ago, have spent the last hour walking across a map from a pea in a hand to a universe possibly infinite in extent. We have talked about structures so large that light takes billions of years to cross them. We have discussed horizons beyond which no signal can ever travel. We have acknowledged that our own position inside a cosmic supervoid may be warping our measurements of the universe itself. And we have done all this sitting still, using only language, mathematics, and the light that telescopes have collected. We have not gone anywhere. No human being has ever travelled further than the moon. And yet, through patient observation, through careful measurement, through the accumulation of centuries of astronomical work, we have managed to perceive, in some dim but real way, the shape of a cosmos billions of times larger than the planet we live on. That is the thing that is most remarkable. Not the size of the universe, not the horror of it, not the isolation. The fact that a creature as small and short-lived and localized as a human can reach out with thought alone and feel the shape of something this immense. The universe is vast beyond description, yes, but the mind that notices it is part of the universe too. Every measurement we have made, every ruler we have bent, every horizon we have calculated, happened inside a brain made of atoms forged inside dying stars. We are, quite literally, the universe looking at itself, a tiny, ephemeral, temporary arrangement of matter, briefly conscious, briefly capable of wonder. And in that brief window, we have managed to locate ourselves on a cosmic map that extends at least 93 billion light-years across, and possibly further than any number can express. That is not nothing. That is not meaningless. That is, whatever else it is, astonishing. Now, let me close with the thing I promised at the start. The title said, "The true scale of the universe is bigger than you think," and it is not even close. Every part of this journey has demonstrated that. The solar system was bigger than your intuition said. The galaxy was bigger than the solar system could have suggested. The local group was bigger than the galaxy could have hinted. The cosmic web was bigger than any supercluster could have predicted. The observable universe was bigger than the web made clear. And the true universe is bigger than the observable universe, by margins we cannot even bound. Here is what I want you to carry away. The disturbing part is not that the universe is big. We said that at the very beginning of this journey. The disturbing part is the pattern. Every time we thought we had reached the limit of scale, we discovered we were still thinking far too small. Every time we built a model, the model turned out to be a miniature of a miniature of a miniature. Every ruler we used broke on contact with the next rung, and the pattern does not appear to stop. There is no reason to believe, from the evidence we have, that any upper bound exists on the size of reality. For all we can measure, the ladder continues. For all we can prove, it never ends. You came into tonight with a picture in your head of the size of the universe. Whatever that picture was, delete it. It was wrong. But do not replace it with a new picture. Because whatever new picture you form, drawing on everything we have just said, will also be wrong. Smaller than the truth. Inadequate to the actual structure. The correct response is not a new picture. The correct response is a new attitude. An attitude of permanent openness. A willingness to accept, whenever anyone gives you a number about the cosmos, that the number is a floor, not a ceiling. That the true figure is larger. That whatever you just imagined, the reality is still more. We are small, that is true, but the smallness is not the story. The story is that the universe, the actual universe, is structured at layers of nested scale that collapse human intuition again and again without ever reaching a final layer. The story is that from where we stand, inside a galaxy, inside a supercluster, inside a cosmic web, inside an observable sphere, inside a universe that may be infinite, we are looking outward through at least 5 concentric shells of wonder. Each shell hides the next. Each shell is dwarfed by the next. And the final shell, the one we cannot cross, hides something we have no way to measure and no way to name. The observable universe is 93 billion light-years across. That is a confirmed number. 2 trillion galaxies. That is an estimate from the best surveys we have. 700 billion at the low end, depending on how we count. Hundreds of billions of stars per galaxy. Dark matter outweighing visible matter by a factor of 5 to 1. Dark energy driving the expansion, accelerating us toward eventual cosmic isolation. A cosmic web stretched across the full visible volume. A true universe beyond that, likely far larger, possibly infinite. And us, inside it all, watching, measuring, naming. 30 trillion cells per human. 8 billion humans. One tiny moment of awareness in the history of a cosmos that has existed for 13.8 billion years and will continue for vastly, vastly longer. You cannot hold this. I cannot hold this. Nobody can hold this. The only honest response is to acknowledge that the universe is too big for the mind that evolved to notice it, and then to do the one thing minds can do anyway. Keep looking. Keep measuring. Keep asking how much further. Keep accepting, with a kind of patient humility, that the answer to every new question about cosmic scale is almost certainly going to be larger than you imagined, and the gap is not even close. Go outside tonight. Find a dark spot away from city lights. Look up. The stars you see are all within our own galaxy. The faint smudge of the Milky Way is one of 2 trillion. Each of those galaxies contains worlds. Each world potentially has its own sky. Each sky, if eyes exist to see it, looks out at the same cosmic web we do. And the web, the sphere, the horizon, and everything beyond stretches outward from every point in every direction to a size the word size was never meant to describe. That is the true scale of the universe, bigger than you think, and not even close.